Alright, so here we have three resistors. We'll call this resistor 1, 2, and 3. And what we'll be doing with these is configuring these into both a series and parallel circuit, where we will find the current that's flowing through each of these resistors as well as the voltage across these resistors in order for us to validate Kirchhoff's rules. In addition to this, we're going to also validate Ohm's law by figuring out, once we get the current flowing through each of these resistors and the voltage across each of these resistors, we can then calculate what that resistance of the resistor is from that information, which in turn gives us Ohm's law. Right? So in order for us to validate that particular part of the lab, what we're going to do is we're going to determine first what the theoretical resistance of each of these resistors is. So I'll just plug these in and use our multimeter to set it to the correct setting, and here it says if it kind of stabilizes, we get about 97.6 ohms of resistance through this particular resistor. All right. Moving on to the second resistor for theoretical resistance, plugging this in. Here at this particular setting, we have it a little too, the resistance of the resistor is too high, so we'll move it to the next setting. And based on our setting, the highest value that we can get out of this is 2k ohms, which is 2,000 ohms. So anything that's written here would be in kilo ohms. So we have 0.481 kilo ohms, or 481 ohms. All right, so that would be the theoretical resistance for resistor 2. Doing the same for resistor 3. Oh, we see that we exceed that, so we'll go to the next one. And we get 2.10 kilo ohms. And so that would be 2,100 kilo ohms. Or sorry, 2,100 ohms. All right. Now that we have the theoretical resistances for resistors 1, 2, and 3, we can use the equations that we've discussed before in order for us to then calculate what the total resistance of the circuit would be if all of the resistors are hooked in series and all of the resistors hooked in parallel. Remember that as a check, but not as something that will definitively say your answer is correct, but just as a check, the total resistance in your resistor connected in series should be larger than the largest resistance of a single resistor in that series. So if you find the largest resistor and the total resistance in series is larger than that, that's a good check that what you have is fairly good. Conversely, with all of our resistors in parallel, when you calculate that, the smallest resistor will be your check, and you will want to make sure that the total resistance of all these resistors in parallel are smaller than the smallest resistance of all the resistors. All right. So now let's move on to the series circuit, and I'll have that all hooked up in just a moment. All right, so here we have our three circuits, 1, 2, and 3, all hooked up in series. So again, what we mean by series is effectively that we will have the current coming out of our power supply, out of here and into our first resistor, then through our first resistor, out, and then into our second resistor, through our second resistor, like such, and then out, and then into our third, and then finally the current flowing out of the third resistor back into the power supply. So we will use a voltage of around 10 volts, and we'll just check that just to make sure it's 10 volts coming out of the power supply. And then with that, we're going to measure the voltage across each of the resistors with the power still on. So let's turn that on. And here we get about 10.09, or we can go about 10.10 volts. Either one is fine. All right, so what we'll then do is leave this on. Shouldn't cause too much damage. All right, and then we'll hook up in parallel to resistor 1 to see how much voltage is going across that one. And we see that we get approximately 0.36 volts. Okay. Next, we'll do the voltage across resistor 2. Here we get 1.81 volts. All right. Hook these, and then we'll hook it up to resistor 3, which has the largest resistance, and we see that we get 7.92. Okay, so that will be the voltage across resistor 2. And when you enter this into your worksheet, voltage S will be the voltage across the power supply, basically indicating that this is for the full series circuit. And we can check that again as well, that hopefully the voltage coming out of our power supply is still the same as the voltage that's running across all three of these at the same time. So let's just check that really quick as a check. And again, we get the 10.09 volts that we started with just out of our power supply. Okay. So the next thing that we need to do is we need to then find the current that's flowing through each of these resistors. And this is going to be a little bit more tricky, as what we'll need to do is we'll need to set our multimeter to run in series with the rest of these resistors. All right, so I'll have to be pulling some wires and whatnot and making sure that the current is flowing through rather than flowing around or across like we were doing with the voltage. Okay, so I've changed my current setting to hopefully read at the level of current that we're going to be using. So what we'll determine first is the current that's coming out of our power supply into resistor 1, and we'll call that current 1. Alright, so let me just set this off to the side like such. Actually, I'll kind of move these out of here since there's so much stuff. Alright, so we have current going into the ammeter. Pull this out. So here we have the current going into our multimeter, or in this case, we've set it to the ammeter setting since we're measuring in amperes. Then out of the multimeter and into resistor 1, and we get 3.77 milliamps. All right, so that's milliamps, so you'll need to divide this number by 1,000 in order to get the correct units of amps, so that we can then apply those numbers using Ohm's law. Right? Next, what we'll do is the current that's flowing out of 1, so along this wire here, and into resistor 2. Okay, so here again, the current needs to come out of resistor 1, like this, into our ammeter, out of our ammeter, and into resistor 2, like such. Right? And we see that we get 3.77 milliamps again. All right, so next we'll get the third current, and then we'll get the current that's coming out of 3 and into the power supply to get our overall current that's flowing through our circuit. So we need out of 2, that's coming out of 2 into our ammeter, out of our ammeter, and into resistor 3. And again, in this case it's a little bit more, well, it's fluctuating more on the high side apparently at about 3.78. You can call it 3.77 if you wish. All right, and again, this is in milliamps. All right, so that's resistor 3 for that current. And finally, we'll get current S, which will be the total current flowing through our circuit in series. And lo and behold, we get, again, 3.77. Right? So in this particular configuration, we see that the voltage changes based on the resistances of each of the resistors and would be proportional to that. Because there's only one loop in this particular configuration, we see that there's only one current, and that current remains constant no matter where we put the ammeter in our circuit. All right, so that finishes the series circuit, and next we will look at the parallel circuit. All right, here we have the parallel circuit of the 3 resistors where we have our power supply providing power and supplying a current coming into here, our first junction that splits off and goes into the next junction below it, and also through resistor 1 and back into another junction on the other side. We'll get to that in just a moment, but this current that has split off to go to resistors 2 and 3 here will then be split at this junction, where some of that current will then flow through resistor 2, and then whatever is left over, hopefully we'll see goes through resistor 3. Coming back through our connections again, the current should then come back into this junction here where it will combine with the current that was going through resistor 2, and then through here back into the junction I mentioned before, where we have the current from resistor 1 joining back up from this current from resistors 2 and 3, and then finally coming back to our power supply, in which we hope that this current, both going through here and here, are essentially the same. We're not losing any current in this particular setup, nor is any sort of large amounts of voltage being lost, as well as also something we'll look at. So in this particular setup, we actually create 3 separate loops with each of the resistors forming a loop with the power supply itself. And the current that's flowing is actually indicated this time by the colors of the wires themselves, where the red wire is indicating that the positive flow of charge is going into our resistors, and the black is showing it going back out into the negative terminal on our power supply. All right, so here what we'll do first is measure the voltages, since that's usually one of the easiest measurements that we can make. Let me just slide this over. And so we have it currently set to approximately our 20 volt setting. So we'll turn this on. And we'll check the voltage again across our power supply. This will be the voltage slash the voltage P. So when you put in the total voltage of the system for P, or parallel circuit, this is how much you would put in. And in this case, we decreased just a little bit slightly from our series circuit, so we're at 10.02 volts across our power supply. All right, so let's find the voltage that's across resistor 1. So we'll need to find the voltage going across. So again, it's going to be parallel. So it's just going to make yet another split off in the junction that we currently have there, and we see that we get 10.02 volts for resistor 1. For resistor 2, to kind of make sure all of our connections are good, because sometimes that may do funny things. Because we're supposed to have, there we go. Supposed to have constant voltage across each of the resistors. And here we see we get 10.02 volts across that resistor 2. All right, just apparently had the current a little too low on the power supply, so that fixed it right up. All right, and last but not least, resistor 3. And we see, lo and behold, we get 10.02 volts. So we see here that Kirchhoff's rules for the loop rule is satisfied, in which each individual resistor forms a loop with the power supply. And since it's just a single resistor with a single power supply supplying 10.02 volts, we would expect that the voltage across each of those resistors to be 10.02 volts. Right? And that validates the loop rule in terms of parallel circuitry of resistors all in parallel. Now next is going to be even more tricky than what we did with the series circuit. What we'll need to do is find the current that's flowing through each of these individual resistors, coming between the junction that we have here and the resistor itself. So I'm going to do a little bit of manipulation of the wires and stuff to make sure that I get the correct current going through and out of each resistor. All right, so what I'm going to have to do is I'm going to have the current flow into our ammeter. We'll set it to the ammeter setting so that we get current. We need it to flow into, so like I said before, our current is flowing out of this wire into this junction and splitting off between those. So what I'm going to do here is I'm going to take this wire, I'm going to take this wire, unplug it for just a moment, and I'm going to insert this wire and recreate that junction I just had before. So basically what I've just done is extended this exposed wire here to the junction that I originally had in this blue terminal before. All right, so that will be helpful in terms of finding what the current is going through resistor 1. Right? So what I'm then going to do is pull this out and have the current that's coming out of that junction into our ammeter. So it's coming out of our junction into our ammeter, and then out of our ammeter back into our resistor. And apparently we are a little too low on the setting, and here we get 105.556, whichever, milliamps So divide that by 1,000 again to get the value in amps. All right, and hopefully you'll notice a pattern here once we go to the other ones as well. Hopefully you might already know what that pattern should look like based on the fact that we know we have our resistors going in ascending order of resistance. So it's going from low resistance to high resistance, and we've kept, or at least we've demonstrated here, that the voltage across each of those resistors is constant. All right, so doing the same thing for resistor 2, we'll get that current. I won't go through the explanation again. You can always go back and rewatch the video if need be. So here I get 20.8 milliamps. Again, divide that by 1,000. Since it's just going to be slightly above that, I can't quite get as much precision as I would like. So we'll just go with 20.8 milliamps. All right, and last but not least, the resistor 3 current. In this one, we don't really have a junction, but we'll still sort of follow the same pattern of determining that particular current. And for just a little bit more precision, we get here 4.77 milliamps. All right, before we conclude with our measurements, the last thing we want to do is we want to measure the current that's coming out of our power supply and into our first junction. And we'll also verify that the current coming out of this, call it a mess if you want, but this is essentially that the currents coming in and out are the same. So we'll check that, and that will be current P. All right, so we'll want the current to come out of our power supply into our ammeter, back out of our ammeter and into our power supply. So let's adjust that, and I see here we get 130.6 milliamps. All right, so let's verify whether or not we get the same amount of current coming out of our parallel circuitry. All right, so out of, into, and we see that we get just a slight decrease in the amount of about, say, 0.9 milliamps, maybe about 0.8. So here we get 129.8 milliamps. And the reason why we're probably seeing this has to do with a lot of wires that we have here. Each of these wires carries a bit of resistance itself. They're not perfect conductors where they have zero resistance, so they'll carry just a little bit of resistance on them. There's also the terminals and things like that, and just some other things that may contribute to the overall process of resistance occurring, like temperature dependency and things like that. So just some things to keep in mind when you are doing your analysis on this. Hopefully this has sort of demonstrated for you that the junction rule is hopefully true, in which that the total currents that we got from resistors 1, 2, and 3 add up to the total current that we see coming out of our power supply. So I would prefer probably to use the first measurement that we got and just treat this one that we got here as just sort of a verification or validation, basically a check on whether or not we're getting hopefully what we're supposed to be seeing here. So, all right, good luck.